Good morning all. We will continue with the application of Gauss law. The third one is infinite sheet of charge. Here if we take a point P on the Gaussian surface, it will be close to the sheet and that point will be small compared to the sheet, hence called infinite sheet. That is why we are calling it as infinite sheet, not because the sheet is very large or infinitely large or has infinite volume, area or infinite length. This not because of that we are calling it as infinite sheet. Okay. Now the point drawn here, actually the point P will be very close to the sheet. Okay. Now to do the analysis, we are drawing it at a certain distance. Okay. Now you assume that you are standing in a closed room and you are holding a textbook perpendicular to the floor in your hand. Okay. And the cover page of your textbook faces towards the right side wall and the back page towards the left side wall, and you assume that charges are flowing from right to left and left to right. That scenario is drawn here. This one is an infinite sheet. Charges are placed here, so it is understood that electric field will be in this direction and in this direction. Okay. That is why E is marked in this direction and in this direction. And these two are the end surface of cylinder. Cylinder has three surfaces, two end surface and one curved surface. First we will see the end surfaces. Okay. Now I am taking a point P over this end surface, and the small differential area D across this end surface will be in a perpendicular direction. That is drawn here in a perpendicular direction. Same is the case here also. If you are taking a point P across this end surface, then the area vector or differential area, you can call it as either area vector or differential area, will be perpendicular to the closed surface. Listen, one point that I have to make clear is you are drawing a cylindrical closed surface here. Cylindrical Gaussian surface here. Even though you are drawing the cylindrical surface here, actually the closed surface is here. This portion will be your closed surface where the charges are enclosed, because from this point to this point there is no charge, from this point to this point there is no charge. This is your charge sheet, and here all the charges are placed. So in this portion only the charges will be enclosed in a closed surface, and from there the electric field lines will be flowing like this. Okay. Now we will see the curved surface. This is my curved surface, and if I am taking a point P here, then it is understood that the area vector will be in a perpendicular direction like this. But the electric field vector will always be in this direction because the charges are flowing in left-right direction. So here you can see the angle between dA and dA is 90 degree. So if you write the Gauss law, E dot dA equal to E dA cos theta, theta 90, so that term becomes equal to 0. That means here there is no flux across this curved surface. First I will find the total flux across the end surface 1 and 2. Psi equals psi 1 plus psi 2. Psi 1 equals E dot integral E dot dA cos theta, and the angle between E and dA is equal to 0, so it will become E dA. E is a constant because it is a uniform surface. That is equal to, so I have taken E outside, E dA integral dA. Same is the case of psi 2 also. So the total psi is equal to 2e integral dA, which is equal to q by epsilon 0, which is our Gauss law. Now, in the case of infinite sheet, it has an area. So we can use charge density rho s as charge per unit area, that is q by A. From that, q is equal to rho s into A. That I am substituting in equation 1. So rho s A by epsilon is equal to 2e integral dA. This integral dA, I can write it as A. So rho s A by epsilon is equal to 2EA. Finally, I will get E is equal to rho s by 2 epsilon 0. As I said earlier, across the curved surface, psi will be equal to 0. So the total electric field is sum of all these three surfaces, that is equal to rho s by 2 epsilon 0 plus 0. Therefore, E is equal to rho s by 2 epsilon 0, and D is equal to rho s by 2 into n cap, where n cap is a unit vector normal to the plane, which is pointed outwards, because you can see here the electric field is in this direction. Okay, so the unit vector also will be in this direction. Now you assume that the sheet is something like this. That is, you are standing in a room, then you are holding a book in your hand, something like the cover page will be facing the top of your room and the back page the bottom, and here the charges are placed. So now here the electric field is in the upward and downward direction. There will be no electric field horizontally, that means right or left of the cylinder there will be no electric field. Okay, here also the same steps you have to follow. You have to find out the electric field across these two surfaces and this one, the curved surface, and finally add. Okay, in both the cases expression will be same. The only difference is in the direction of unit vector. Okay, because here the unit vector is in the upward or downward direction. Earlier case it was in a horizontal direction. The expression will be the same. Next we will see the electric field of uniform charge sphere. Sphere is of two types, solid and hollow. Solid, watermelon, hollow ball. Now here you will see electric field of solid sphere. Since a sphere is solid, it is completely filled with charge. Okay, that means it has a volume. So here you can see a sphere whose radius is r. Since it is filled with charge, it has a volume. So we will take the volume charge density rho v equals q by v, that is equal to q by 4 by 3 pi r cube, where 4 by 3 pi r cube is the volume of sphere. From that, q is equal to 4 by 3 pi r cube rho v, and this is the net charge of this solid sphere. Now here we have to take two cases. In first case, what I am going to do is, I am going to draw a inner Gaussian surface here, this one. This is my solid sphere and this is my inner Gaussian sphere. This is uniform. Okay. Now here capital R is the radius of my solid sphere and small r is the radius of my Gaussian sphere, such that small r is less than r. Now one important thing that you have to keep in mind is, inside a sphere which is filled with charge, at different points the charge density will be different, because the charge density depends upon the distance. Because if you are measuring a charge density here, that will be different from the amount of charge placed here. Okay, so that means if capital Q is the total charge of this solid sphere, then this Gaussian sphere will be having a different charge, and that is taken as Q dash. And here Gaussian sphere is also a solid sphere, so it has volume rho v equals Q dash by V. From that, Q dash is equal to rho v into V, and rho v is equal to 4 by 3 pi small r cube, because this rho v is the volume charge density of our Gaussian surface, and the radius of our Gaussian surface is small r, hence 4 by 3 pi r cube into rho v. This is the net charge of our Gaussian surface, and I am writing the Gauss law E dot dA is equal to Q dash by epsilon, because I have taken Q dash as the charge, and the point to be noted is dA is the area vector of Gaussian surface. Okay, that you have to keep in mind. And E dA cos theta is equal to Q dash epsilon 0. Here across this on this Gaussian surface, I am taking a point P, and as I said earlier, the area vector will be perpendicular to dA, and this positive electric field will also be perpendicular to this surface E, so that E and dA will be at an angle theta equal to 0. So you will get E dA equal to Q dash by epsilon 0. Since the Gaussian surface is uniform, E will be a constant. E integral dA equal Q dash by epsilon. The area of sphere is E into 4 pi r square is equal to Q dash by epsilon 0. From that you will get E, which is equal to Q dash by epsilon 0 4 pi r square, which is the electric field inside the solid sphere, because here Gaussian surface is taken inside the solid sphere, so the expression you are getting is E in. Okay, now here we have the expression for Q dash that you can substitute in this value, and finally you will get E in is equal to small r into rho v by 3 epsilon 0. Now in the second case, what you have to do is you have to draw a Gaussian sphere outside our solid sphere. Okay, so this is a solid sphere of radius r, and this one is a Gaussian sphere of radius small r, such that r is greater than capital R. Now here, what will be the charge of our Gaussian surface? Now we have already studied that if there is an inner surface having a charge q, then that charge will be transferred from this surface to the outermost surface by means of our electric field lines, that is flux. That means if this charge is having plus q, then if this surface is having plus q charge, then this surface will also be having same charge with opposite polarity. Hence, the charge across the Gaussian surface is capital Q, which is same as our solid sphere. Hope the concept is clear. We have already learned earlier the Faraday's experiment. You have to keep in mind, that is, there was an inner circle which was charged with plus Q, and there was a outer circle which was initially neutral or otherwise grounded. So what happened is, due to the effect of this inner charged wire, the outer wire also got charged with opposite polarity. The same theory is used here. So this and this, both the surface will be having same charge. So integral E dot dA equal to Q by epsilon, then E dA cos theta equal to Q by epsilon. Here when you are taking a point across our Gaussian surface, what happens? E will be like this and dA will be like this. So both of them are at an angle theta equal to 0. So theta equal to 0, and this capital Q is same as that of our solid sphere, that we will be substituting here. So you will get E dA cos theta is equal to 4 by 3 pi r cube by epsilon 0 rho v. Since E and dA, the angle between both of them are 0, you will finally get E integral dA is equal to this much. Then area of sphere is 4 pi r square. Substitute that, and finally you can rearrange it, and this will be your expression, and that is your E out, because the Gaussian surface is outside the solid sphere.